Only around 20 significant nuclear reactor accidents have occurred globally since commercial reactors were first built.
Nobody really knows and understands 100% what goes on in the nucleus.
Over 8 million people around the world died prematurely from illnesses related to fossil fuel pollution.
If the energy imparted by the extra neutron exceeds the binding energy of that nucleus, it splits in two. This supercritical mass can be such that too much energy is produced, you create an explosive.
We do fear that with which we are not familiar or have no intimate understanding. Welcome to Under the Spell, a curated podcast series that explores the ideas behind the book by the same name. Now, the book has been divided into 5 sections, each named after one of Hesiod's 5 ages of man, a structural choice that really mirrors the recurring rise and decline that underpins the broader historical narrative of humanity over these periods. And across these 5 parts, the book has developed 2 long and continuous narratives that really are interwoven throughout the book. We firstly got the Malthusian narrative and the story then also of Western philosophy, which follows the shifting understanding of truth, morality and human nature from antiquity all the way through to modernity. And today we turn to perhaps the most controversial energy technology ever developed, nuclear power. In the early decades of the atomic age, there was genuine optimism that nuclear energy might be the world's dominant power source. The promise was extraordinary: enormous amounts of electricity, virtually zero greenhouse gas emissions, and fuel supplies that could last for decades. But as we know, the story didn't evolve that way. And I think the spell describes that nuclear technology became entangled with the politics of the Cold War and the trauma of Hiroshima and Nagasaki, and later the shock of accidents like 3 Mile Island, Chernobyl and Fukushima. And over time, fears surrounding nuclear weapons really merged in the public imagination with nuclear power itself, creating a powerful social and political resistance to the technology. And yet, at the same time, nuclear energy has remained one of the lowest carbon sources of large-scale electricity ever developed, and a number of countries, from France to China, continue to rely heavily on it as part of their energy systems. So how should we think about nuclear power today in a world that is trying to decarbonize? Well, to help us unpack this, I'm joined by someone who spent much of his career at the heart of the nuclear industry. Professor Johannes Slabber is Professor of Nuclear Engineering at the University of Pretoria. He's got decades of experience in reactor design, nuclear safety and energy policy. He served as Chief Technology Officer of South Africa's Pebble Bed Modular Reactor, the PBMR, and he's worked with the International Atomic Energy Agency in Vienna on nuclear safety. So I must say it's a real pleasure, honor and privilege, Professor Slabber, to have you onto the podcast. And let's just kick off on that framing that I introduced the series with, in that what seems to have happened is there's been this interweaving of fear around nuclear power, where almost it's as if the world, being introduced to electricity via the electric chair, became scared of it because some of the accidents that we saw around 3 Mile Island and Fukushima and that. To what extent do you think that historical association still shapes the way society thinks about nuclear power today?
Well, thank you very much, first of all, for having me and to share my passion with you and the listeners and the viewers. And as you've rightly said, I believe right from early on that nuclear power is really a clean power, and one needs to understand what lies behind the nucleus and the nuclear power, the using of the nucleus in atomic in the atomic world, as well as utilizing what powers are actually contained in the nucleus of all elements. So particularly a few of these elements have very peculiar characteristics, and they emit radiation. They can break up in two, etc., etc. But to answer your question, nobody really knows and understands 100% what goes on in the nucleus. Even the wisest reactor physicists still speculate. So the entire nuclear scenario is actually surrounded by an uncertainty, and the people and the population is really uh, uh, sort of engulfed in a cloud of uncertainty. And if you don't understand exactly what is going on, you tend to be afraid of that. And that is what happened after it was introduced in Hiroshima and Nagasaki. There was a lot of radiation, and suddenly people started becoming ill, and it looked like a mysterious effect that engulfed them, and that uncertainty and that not knowing exactly what is happening is really still today plaguing the population as a whole. So if I don't understand it, I rather shy away and try not to think of using it in general. So I believe it's mainly because of a lack of knowledge.
Often when you actually look at issues in the world, it is down to something as fundamental as that. There's
Yes.
a huge kernel of truth in that we do fear that with which we are not familiar or have no intimate understanding. So let's address that, because you said, I mean, a lot of anxiety comes from the word nuclear itself. From a scientific and engineering perspective, how fundamentally different, firstly, are nuclear reactors from nuclear weapons?
First of all, if I need to explain something. First of all, that the power that is contained in the nucleus of especially certain heavy elements like uranium, plutonium, which is an artificially produced element, and thorium is actually located in the energy, what is called binding energy, and that is the energy that binds a nucleus together. It A nucleus must consist of two fundamental particles. I say fundamental particles that to explain it to the uninformed people. They're really seen as particles, but they can also behave as waves. So there's already an uncertainty there. But in any case,
Yeah.
let us go back to the engineering field and say the nucleus, and that is why we're talking about nuclear power, not atomic power, nuclear power. The power is really contained mainly in the nucleus of an atom. Uh, and that energy is created by the binding together of these particles, which we call nucleons, but they are protons, which define the element, and the neutrons, which is an uncharged particle, but its effect is to bind a nucleus of all elements together, because the proton has got a positive charge, and you can't
Yeah.
join two positives because they'll just be ejected. So you
Repel.
need
Yeah.
somebody to calm down the nucleus, and that is done by neutrons, and that's a very important particle to have. You can have a nucleus that is bound together, and it's very stable. So the neutron effect on the particle itself to bind it together, and there's no unbalanced energy. But if you add a neutron, you can upset the balance in the nucleus. If you add the neutron, there is excess energy created, and this neutron becomes what is called radioactive, and it needs to emit energy. But if the energy imparted by the extra neutron is exceeds the binding energy of that nucleus. It splits in two, and when it splits in two, it releases extra neutrons because the nucleus feels that there's too many neutrons. So that is what's happening in the nucleus of a heavy element like say uranium. Now, to answer your question, this energy is utilized, can be utilized to produce power if you've got enough of these reactions taking place, and you get that by using the neutrons that's being emitted after the breaking of this particle, which is called fission, breaking in two.
Yes.
The neutrons that is released because there's too many neutrons. But now that neutron can enter another nucleus and cause the same reaction. And that reaction can cause another reaction. So one can
that's the
get
chain
what is
reaction.
called a chain reaction. And each of these reactions emit a lot of energy. And because it's so small and a piece of material contains such a lot of these basic nuclei or nucleus in plural, you can create a lot of energy. And if you've got enough of that material, this can cause what is called a critical mass. Critical mass is a self-sustaining mass of this heavy material that is emitting and producing power. And if you add a little bit more material, you create a supercritical mass. And this supercritical mass can be such that too much energy is produced, and it can either heat up, melt, and then spread out, or if that energy is added too suddenly, and the mass cannot follow as a result of inertia, you create an explosive. So that's the difference between a reactor using just enough material and removing the energy produced gradually to produce power by means of turbines, steam and turbines, or you can have too much of this material too long together, too much energy is produced for this material to move. It's like taking, say, for instance, a balloon, and you blow it up, and you put energy in it. It blows energy, and it still stays, and it blows up until a time when it can't contain it anymore. Then it just blows apart. So what you need is the difference is that in the one you're using the energy, and you design it such that the energy is gradually taken away, and the bomb or explosive is that you keep it together for a long time, and you supply enough material so that the buildup of energy is very high, because the time between one reaction and the other reaction is very, very short. So you need to contain this material just for a couple of milliseconds. Then there's enough energy. It's like it's a glowing ball of plasma, and then due to radiation and other pressures, it just flies apart. And that is the bomb. And the other, where it's designed that the energy can be taken away gradually, is a reactor. But all the energy is produced in the nucleus.
It's fascinating. So it shows why the physics of electricity generation would then differ from the physics of nuclear explosions, because what you're trying to do when you're generating power is to ensure that you have a stasis or a balance to avoid that that scenario of overfilling the balloon and having nowhere for that energy to go and then creating an explosion. Fundamentally, what would you say are the basics when it comes to design principles to ensure that we can produce nuclear energy safely today?
I would say that there are a number of reasons or objectives that one needs to have in mind when you design for future reactors, and especially for safety. And that is that you should actually take the failure of operators out of the question. In other words, you must assume that an operator of a reactor will fail 1 in 10 operations. Then you must design your reactor such that you do not rely on the operation of engineered systems to keep it cool, because maybe I can just take a step back. You need to have a medium that can take the energy away into the system to use to produce power. But if you do not have that, and keeping in mind that every breaking up of a nucleus into 2 parts creates 2 new elements with an unbalanced proton-neutron relations or balance, and they are very radioactive. They are called fission products produced by the fission reaction. And they also create heat, because of the radiation is not something funny. When it's absorbed, it creates heat, and the heat damages anything. It heats up material in the reactor, or if it's out in the outside, it impinges on a human cell and damages the cells, and that is how the damage is created, by the deposition of energy. Now, to come back to my answer to your question, the fission products are actually created in the fuel of a reactor, and they will keep on heating. Although you can switch off the nuclear reaction, they will keep on heating to a lesser extent, but they must be the fuel must be cooled. So even after the reactor is shut down. So to get back to future reactors, one needs to take the operator out of the question. In other words, to rely on the engineering design. But the engineering design must also assume, and it's proven by statistics, that a design can fail anytime. No design is foolproof and operates 100%. Sometimes your brakes fail in your car, your steering fails, or a tire bursts, etc., that can cause an accident. So in a reactor, it's the same thing. You must always assume and design that the reactor core can be cooled anytime. Even after the reactor has been shut down, you must be able to take away the energy produced by the fission products that's still present in the fuel. So you cannot, for future reactors, you should not allow the design to rely on active cooling systems that must start up, pumps that must start up, valves that must open up, etc., because they can fail. So you must design your reactor that even if all cooling, but normal cooling is removed or stopped, the design is such that nature, which never fails, nature can allow the heat to be removed, because if you don't remove the heat, the fuel itself can lose its integrity and release the radioactivity that's produced in it into the environment. So you must have your reactor design that you have inherently safe characteristics. And the main aspect is to cool the core inherently during totally upset conditions.
How would one go about designing that? And I think aligned to that, maybe it's a separate question. But I've always found it fascinating when you go back and you look at the history of the development of nuclear power. It's not a fait accompli that we wound up with uranium. Thorium, as you mentioned earlier, you mentioned thorium is also used in nuclear power. Now, from what I understand and from what I've read, it's a very layman interpretation, but from what I could see is it's very difficult to turn thorium into fissile material. In other words, to turn it into bombs versus uranium, and we know the story there. And so the development of thorium reactors was curtailed to some extent because of that, but they are inherently safer in terms of the fuel source. I mean, what are your thoughts on that?
Yeah, I can maybe do a little bit of an explanation here. Thorium, you can fission a thorium atom, but you need a very high energy neutron to do that.
Oh.
They call it, thorium is fissionable. And uranium-235, which is an isotope of uranium, is fissile. The difference between these two terms is that you need a high energy neutron to fission a fissionable material. You need, and you can have a very slow neutron, and they call it a thermal neutron. A neutron at a velocity that is in thermal equilibrium with a medium, because it's born after this fission reaction as a very energetic neutron. But then it needs to be moderated. Its energy needs to be moderated in the medium that you supply. If you have, and then it loses energy by interaction, scattering reactions in the moderator until it gets to an energy which is about eight orders of magnitude smaller than the energy at which it was born. And then it enters as a thermal neutron into the nucleus of a U-235 atom, isotope of uranium, and then it fissions. And these are called thermal reactors. If the core is constructed out of, say, uranium-238 or thorium, you can actually make it fission and keep the neutron population at high energy, and those reactors are called fast reactors. That's just a little bit of background. To come back to your question about thorium, thorium is fissionable, but what happens and why thorium is so valuable in future is that you can breed an isotope of uranium by the capture of a neutron into the nucleus of thorium, and then the radioactivity that you're creating, as I mentioned, allows this thorium to release radiation in a way that the element of thorium or the new isotope of thorium that you're producing by capturing a neutron decays, it releases energy, and then it changes also the element. It changes back to uranium again, and it changes to uranium-233 isotope, which is it's a fissile isotope. In other words, it can fission by means of a thermal neutron. So what you have, if you use thorium in your reactor, you put it there to create fissile material by capturing a neutron and then decaying into uranium-233, which is fissile. So they call it breeding. They call it breeding. The uranium-238 isotope is also fissionable, but it can also capture a neutron, change to uranium-239 and decays, and that becomes plutonium-239, which is actually also a fissile material. So those reactions are actually present in breeding reactors, where you breed fissile material. So in future, and especially the Indian, they've got a lot of abundancy of thorium in India. They're focusing on going the thorium breeding route, where you actually put thorium in your reactor, and while you're operating this reactor, this thorium changes to uranium, which can lengthen your fuel cycle in your reactor. So it's got its positives, but it's got a very big negative. And because the uranium-233 is a weapons type material. If you have sufficient uranium-233, say for instance 15 kilograms of that, you can build a very sizable atomic explosives with that. So the focus on those type of designs is such that you keep a very big a magnifying glass on the knowledge of where that material is and in which country that material is being created.
Yeah, as we've seen with what's going on in Iran at the moment, and making sure that material like that doesn't end up in the hands of bad actors globally. I want to come back to the legacy of nuclear and events like 3 Mile Island, and you mentioned, how we ensure we have safer reactors. Well, Chernobyl, anybody who's watched that excellent documentary on Netflix will see there was a lot of human failure in that. Fukushima, very much a natural disaster, earthquake, tsunami. It still probably withstood that fairly well, given what was thrown at the reactor. But I think they loom large in the public memory and the public eye. And the spell notes that only around 20 significant nuclear reactor accidents have occurred globally since commercial reactors were first built. So how representative are these disasters of the actual risks of nuclear power when you're to look at, how many people, say, for example, die from lung diseases as a result of coal mining, for example, in the coal-fired power industry? Are we getting the full picture of the true risks of nuclear across publicly?
The entire debate around nuclear is so infused with uncertainty, and people see activities around Fukushima and Chernobyl and 3 Mile Island, and it's cloaked in uncertainty. What are they doing, and what is in the air around them? What are they exposed to? But if they had the knowledge, they would know that what is there is radiation, just orders of magnitude of radiation that they are exposed to on a daily basis. But those are only at those outliers, which I say are the accidents or the incidents that happened. So the big fear is created still by the uncertainty. Now, can I also eventually be exposed to that if a reactor that's close to me explodes or melts down? And as I said in the beginning, the whole fear drive is because the basic understanding is not evident. However, coming back to those designs, they were of a design which actually did not cater for all the events that can eventually engulf the reactor. the event at Fukushima is caused by a natural disaster, but it could be averted if they had the cooling systems, which was actually designed to keep the core cool. As I said in the beginning, you still need to keep the core of a reactor cooled after any event by means of some way. But those reactors, and even the reactors that's in use today, rely on what they call emergency core cooling systems. Unfortunately, in 3 Mile Island, it was human error. In Fukushima, it was a total design error, because the poor pumps that were supposed to pump coolant through the core after the tsunami, after the earthquake, were engulfed in water because of the height of the tsunami. They couldn't operate. All the switchgear was drowned. So the core was actually in water, but after a time, this heat that still remains in the core, after the reactor is shut down, it heats up the core so that eventually it boils dry, and when it boils dry, the core melts. So all those events are not in the public eye, and they are really unsure what happened. And if you're unsure, you skepticism sets in, and then they say, but there's something hidden from the eye, and if I don't understand it, I'm not going to accept it. And and all boils down to a lack of knowledge. And I must say that there is no concerted effort in any country, to my knowledge, that you start telling children what is nuclear power in a very uncomplicated way, and gradually get the message into the minds of people that this is what can happen, this is what's going to happen, etc., etc. And then also tell them that the future reactors, defined by the Generation 4 International Forum, is focusing on inherent safety or enhanced safety. It's always enhanced safety. And that is the big drive at the moment.
I was going to ask you what the biggest lessons from those incidents were for the nuclear industry. And as you've mentioned, it's the Gen 4 reactors and looking at safeguards to prevent these kinds of disasters occurring again in the future. But just back to your earlier point, how do you design a system then that doesn't necessarily... so on the one hand, you've catered for the fact that you're trying to remove human error from the equation. Then the engineered cooling solution could fail, so you want to make sure that it can just cool naturally. How would you design a system to do that?
Your construction of a reactor core consists of the fuel, and then what is called the cladding material, which is around the fuel to stop or inhibit the release of any of the fission products created while the reaction is in process. Because, as I said, the uranium atom becomes a new element, and they are very radioactive. And they must be kept at the point where they were born, and that is right in the fuel. And what you have is then a clad or a protective layer around the fuel that will keep the radiation or those new elements inside. And you must design your cooling system so that the heat can be removed from the fuel after the reaction has been shut down, or the fission reaction has been shut down. How can that be done? Now, the current day reactors are using water to get the. But if you stop the water from flowing, then it will transmit the heat through conduction to the outside. But in the process, it also heats the water and eventually it starts boiling. So that doesn't help. So you must have a medium which is actually such that even at high temperatures can remove this residual heat or this decay heat or this after heat inherently. Now, the solution nowadays, or the solution that we employed and is being employed in future designs, and I know that some of these designs are already on the drawing board, is that use a medium like graphite, which you find in reactors like a high temperature gas cooled reactor. The gas removes the heat during operation, and the moderation or the slowing down of the neutrons, as I mentioned, is done in the graphite, because you need a material with a low mass, a low atomic mass, to absorb energy while this neutron is moderating from the fast energy to the thermal energy. And as I said, water is being used in the current day reactors, but in the gas-cooled reactors, the cooling is done by gas, but the gas doesn't moderate. The graphite moderates. So if you lose the coolant, or the graphite or the helium or the gas is stopped, the heat is removed by the graphite, which has got a very high, appreciably high thermal conductivity to the outside of the reactor. So in these designs, you can easily design for inherent removal of the residual heat. And those reactors are called unmeltable reactors. And this is the method that we employed in the pebble bed modular reactor. So nature ensures that the heat will always be taken away. You don't need to start any pumps. It is there to remove the heat, and the thermal conductivity will not fail you. It's built in by nature and created by the Almighty God that we can use it. So let's use it.
It's fascinating, and I want to come back to the pebble bed modular reactor, but just, to stay on this issue of designing for failure and improving safety, we did see a landmark study conducted, I think, by Harvard University back in 2018 that found over 8 million people around the world died prematurely from illnesses related to fossil fuel pollution. So that equates to roughly 20% of total global deaths for that year, implying that burning fossil fuels is responsible for as many as 1 in 5 deaths. When we compare nuclear power to coal or oil or gas, how do the health and environmental risks actually stack up?
I must say that that study really also fascinated me, and I can believe it, because if you burn something like coal, then you are creating carcinogenic, you're releasing carcinogenic compounds into the air. The smoke contains carcinogenic. I mean, a smoker inhales smoke, and that has the possibility of creating a cancer. Although there's some other chemical effects as well in smoking, but the effluent that is discharged through the chimney contains, in the first instance, this burnt coal substances, which is carcinogenic, and what is even more risky is that the coal itself contains an element, actually a gas, called radon, which is a gas which you can't escape from. Every person, where you're sitting at the moment, where I'm sitting, in a concrete building or any tiles that's made from earthenware, contains radon, and which is actually created in the in during the entire time that the Earth was created, due to the decay or the breaking down of these heavy elements, because uranium, thorium, and all these what they call actinides are naturally radioactive. And when they are releasing their energy due to the release of radiation in the form of what they call alpha particles, beta particles, and electromagnetic radiation, they change elements. They become different elements in this release of energy in the form of radiation. They become different elements because some of these radiation contain protons, and if you release a proton from the nucleus, it becomes a new element. So new elements are formed in the millions of years that this uranium was actually decaying, and eventually it ended up in a gas, what is called radon, which is radioactive, and it's surrounding you where you're sitting and where I'm sitting, and the radiation that you are exposed to, 55% naturally, 55% of your radiation comes from radon. Now, coming back to the release of gas from a coal-fired power station, this radon is then in a concentrated form also part of the effluent that goes up the chimney. So it's a carcinogenic compounds plus radon, which is now spread out. And if you should request the National Nuclear Regulator to regulate a coal-fired power station in the same way as they regulate a nuclear reactor and they put radiation monitors, they would not give a nuclear license to a coal-fired power station. So that is the crux of the matter. The normal release of radiation from a coal-fired power station is orders of magnitude more than the allowable release from a nuclear power station. That's the answer.
Wow. Remarkable. Well, I mean, it shows, therefore, that nuclear power is unfairly judged by a different standard of safety than other energy sources. And so probably fair to say that it again comes down to this fear and this lack of understanding. How would you say the suspicion and fear of nuclear technology historically have impacted policymaking decisions related to the development of nuclear power? And how does that then intersect with the growing fear of climate change at present? Are we seeing a shift in public opinion about nuclear energy as climate concerns grow and as increasingly we see how difficult it is to decarbonize energy systems, even with the rapid deployment of renewable variable energy sources like wind and solar? We are still stacking energy sources on top of other energy sources. We're not replacing the coal and the other fossil fuels underneath them.
Yeah, maybe coming back to a little bit basics before I answer your question in fully. The knowledge base of the regulators worldwide, or the nuclear regulators, also was created, and it was a function of time. In the beginning, if you need to regulate something, you take the worst case and you build your defenses, the regulation and the regulations around that type. But gradually, more knowledge was created during the development of nuclear power, and the regulations sort of evened out. But then suddenly a number of occurrences happened, like 3 Mile Island and Chernobyl and Fukushima, and suddenly there was an outcry of the public, and suddenly the regulator started because they are also, I mean, nobody knows everything. Even the regulators, they based their regulations on information that's gleaned from all that's been published and available. So they tighten up. Suddenly, they tighten up their regulations, and they specified regulations that's nearly undoable. They said, okay, we will allow water-cooled reactors, but then it must be inherently safe or passively safe. You must not rely on motor starting or valves that can open, etc., on an electrical signal. They said we must have big tanks of water on top of the reactor so that you can only open a valve and the core can be cooled, etc. So these regulations stacked up on top of each other and eventually made the reactors unbearably expensive due to a lack of technical insight, first of all, but then came the so-called solution. Yeah, let's not focus on nuclear anymore so much. Let us and in the light of decarbonization, let us now try to use nature to help us, and in a way, not to remove the heat, but to use it as a source of power. But it's got its negatives because it goes up and down on a daily basis, and it's dependent on cycling weather conditions, etc., etc. So the decarbonization actually reached a point at this stage in Europe where there's a lack of most of the time a lack of power available, and importations must be taken from France, which uses nuclear, etc., etc. And at the moment, I think they're at a point where, wow, if we have not stopped our nuclear power in Germany, we would have been in a better place. So it's a total systems approach that is causing a big turmoil at the moment. I don't know if I'm answering your question, but it's an interwoven argument
Yeah.
at the moment. You've got the environmental low power density solutions because you're covering a lot of land and you're covering a lot of space for the cells, the photovoltaic cells, and the wind turbines. They look ugly. So there's a little bit of a realism creeping in at the moment, and one huge problem is that you do not have what they call inertia in the system, because you need to produce power at a certain frequency. And if you're not producing it at the correct frequency and you're slipping out of the allowable band, you've got a total collapse of the entire system. And then you get something that happened in Spain last year. A total blackout.
Yeah,
So
yeah.
and that's costing the economy billions and billions per day. So taking all these things into consideration, there is a huge, one can say, a huge turn of momentum towards nuclear, and then Big Daddy, and I say Big Daddy America, is actually at the forefront of turning the anti-nuclear vision more towards being pro-nuclear, and the world is going to follow. I'm certain about that. That the world will be following America's attitude towards nuclear again, and it's not going to be long before Europe will change, and I think Germany must feel very sorry, very, very ashamed actually, that they've shut down all their beautifully designed reactors, the so-called convoy reactors, in favor of wind and sun, solar, and also coal-fired power stations, which emit a lot of lot of poor products,
And,
bad products.
and geopolitically, when Russia invaded Ukraine, they were overly dependent on gas from a potential geopolitical adversary, and that could be turned off almost overnight. And it did expose those decisions to shut down the nuclear plant of the industrial heartland of Europe. I think there are
Yeah.
a number of other reasons that Germany has slipped behind China in the automotive sector as well. But I don't want to go down that particular rabbit hole just now. When you spoke about the interesting effect that this regulatory stack has had on the cost of nuclear power. So just talk to me about, because a lot of people when you talk to them about nuclear and you say, well, how are we going to decarbonize the world? Here you've got this power that is almost universally abundant. It's zero emissions, but it is expensive. I mean, if you look at Hinkley Point, for example, if you look at a lot of nuclear projects tend to go over budget and over time. So what do you see as the cost implications of nuclear power compared to other energy sources? And would it start coming down if we did see that pendulum swing and we saw a lot more favorable nuclear development around the world? Would that start to bring the unit economics of nuclear power down?
Yeah, if you look at the business case for a nuclear power plant, and a big cost driver, of course, if you compare nuclear power with coal fire, for instance, nuclear power, because of the regulations and some other factors, is capital intensive. In other words, the capital cost of a nuclear station overrides by orders of magnitude the running cost, in other words, the fuel cost. Fuel cost for a nuclear station is rather small compared to the capital expenditure. You've got to mix that all into eventually calculating your cost of electricity. In a coal-fired station, you've got the negative of the high running cost, because you've got to transport your coal or your oil or your gas to a fossil-fired power station, and relatively speaking, the capital cost is lower than a nuclear plant. So you've got to fold that all into your business case to determine your eventual cost of electricity. Now, the big negative of nuclear, if you consider that as your future power generation, you've got to look at the capital cost to reduce the capital cost, first of all, or the duration in which the capital cost is unproductive. Because for your expenditure, you must get something back eventually. So normally, with taking into consideration all the regulations and the additional systems that must be added to your nuclear reactor to keep it safe, causes the capital cost to escalate. So you must actually try and make a design that is not so burdened with extra safety systems. In other words, try to focus on inherent safety. Work towards say for instance, typically a high temperature gas-cooled reactor, which you can design to be inherently safe. A water-cooled reactor, you must actually provide a cooling to make it to avoid the core from melting down. So that is the one thing, to try and reduce the burdensome multiple safety systems. That's the one. Secondly, you must try to reduce your unproductive construction time, where you're not gaining any revenue from your for the money that you've loaned. And the only way to do that is to to make it much more manufacturable in series. And the only way to do that is to reduce the size of the unit that's producing power. In the early days, they focused on the economy of scale. We said, okay, let's build it bigger and bigger, because then you reduce the cost per unit electricity that's produced, because there's certain common actors that's common even if you've got a small reactor or a big reactor. So let us make the reactors bigger and bigger, and we get the benefit of the economy of scale. And that is why we're ending up with this 3,000, 4,000 megawatt monster units. But what accompanies that is construction time. These big units take 6 to 8 years to start operating, and sometimes longer. And during all those times, those billions of dollars are being unproductive. So the focus, that's my opinion, and I've got sufficient information to support that, is that why not go for smaller units, even if you're out of the domain of economy of scale, but build them consequential and start operating, and then while you're building the next one, you're starting to produce revenue. And so the drive in future will be for inherent safety and for smaller modular reactors that can be built in a shorter period of time, and also to enhance the quality, because then you can construct more of the subsystems supporting your reactor in factories and cart them into the field, other than building everything in the field and having problems with weather conditions and quality assurance, etc., etc. So my view is that the smaller, modular, in other words, they are exactly the same and they do the same, but they can be installed one after the other, and the second or the third one can start paying for the expenditure of the next one. So I believe small modular reactors, inherent safety, will be the future savior of nuclear power.
I can't wait to unpack that with you, Professor Slabber, in part 2, because sadly we've run out of time. But this, I think, has been a great introductory conversation into how we get to that point. In part 2, maybe we can go back into some of the historical development of, in particular, the pebble bed modular reactor, which really was leading the world at its time. And sadly, our decision to pull the plug on that. But where we are heading, we are seeing these small modular reactors being piloted around the world with some very encouraging results so far. And then maybe we can also touch on the difference between nuclear fusion and fission, because there's also, I think, a lot of misunderstanding around that as well. But Professor Johannes Slabber, thank you so much. We're going to have to leave it there for part 1. Thanks for your time.
Thank you. It was a pleasure.
Well, if there's one theme that runs through this conversation, and indeed through the pages of the spell, it's that our energy choices are never purely technical decisions. They're shaped just as much by politics and culture and psychology as by engineering, and nuclear power may well be the most striking example of that dynamic. On the one hand, it's an extraordinary technology capable of producing vast amounts of electricity with almost no greenhouse gas emissions. On the other, it remains deeply entangled in the fears of the atomic age. And I think, as the spell points out, decades of living under the shadow of nuclear were certainly blurred by the fear of war and the distinction between nuclear weapons and nuclear energy in the public imagination. And that embedded a powerful suspicion of nuclear technology that still influences policy today. And yet the paradox is hard to ignore. At the very moment when the world is urgently searching for reliable low-carbon energy, nuclear remains one of the few technologies capable of delivering that at scale scale, continuous power without the emissions of fossil fuels. So perhaps the real question facing policymakers today is not simply whether nuclear power is safe or economical, but whether our collective perceptions of the technology have kept pace with the realities of modern reactor design and climate urgency, as well as energy security as well. You've been listening to Under the Spell, a podcast exploring the forces that shape our global energy system and the narratives we tell ourselves. If you've enjoyed this conversation, please follow the series and share it with someone interested in the future. I'm your host, Michael Avery. As always, take care.